Hello, we are FLUX Engineers, an engineering consulting firm that specializes in structural, mechanical, and electrical design. This is our design development for Texas Tech Sports Performance Center. We'll begin by introducing our team and the project, followed by the structural, mechanical, and electrical designs, integration, followed by a conclusion.
My name is Dana Anderson. I'm the structural team lead, and I've been working with John Berggren, Joseph Crow, and Tyler Jorgensen.
My name is Danielle Pasalia. I'm the mechanical lead, and I've been working with Mark Wilder.
And my name is David Repair. I've been working with Justin Mensch, Nick Garay-Cochea, and Zach Larson.
Prior to beginning the design of the facility, we worked as a team to understand our dynamic in terms of strengths and weaknesses. To do this, each member participated in the Gallup Strengths Finder test. Their individual strengths and weaknesses are then shown here on this graphic with the small bubbles. The large bubble represents the collective of our team. From this, we were able to determine we had strengths in executing and strategic thinking, with weaknesses in influencing and relationships. From this, we worked to understand and learn how these strengths and weaknesses could benefit us as a team. To execute sharing information efficiently, we utilize applications such as OneDrive and GroupMe. This allowed team members to be reached from any location, as well as to work from any location with internet access. In addition to this, we implemented weekly interdisciplinary work sessions. These reduced clashes and allowed problems to be solved quickly and efficiently. It also encouraged collaboration between disciplines while increasing work efficiency and stimulating creativity. A result of this was our integration implementation matrix. This matrix included the ideas from each discipline that we then evaluated the pros and cons of prior to implementing within the facility. This allowed us as a team to determine whether or not the ideas were feasible for the project. Shown here are the multiple different applications we use to aid in the design of the facility. A focus for this diagram is our central Revit file. This is where we modeled everything in the end. We use different Revit models per each discipline to eliminate traffic in one model. This allowed each discipline then to have their own sections, views, sheets, and it not be confusing and all within one model.
And now to introduce the project. Texas Tech Sports Performance Center is a 155,000 square foot facility located in Lubbock, Texas. Its overall budget is $48 million. Some of the amenities of this facility include a FEMA-rated safe room located on the west side of the building, a 200-meter indoor track underneath an ETFE roof, and an 80-yard practice field under a photovoltaic array. This facility will also have the ability to host Big 12 championships. ETFE will be mentioned throughout the presentation. For a quick description, it is a fluorine-based polymer that is known for its excellent electrical and thermal properties, as well as its excellent tear resistance. It is an up-and-coming product that is being seen in sporting facilities worldwide. Some architectural changes had to be made to implement the designs of our engineering team. One of the most standout changes is the extension of the west wall, giving us room for our safe room under the bleachers, as well as an extra mechanical space. These changes will be spoken more in detail in the integration section. The project goals go in line with what our client wanted for this facility. They wanted an economical design that kept life cycle costs low, a resilient structure that would be a safe haven for students and faculty to go to during natural disasters, and a high-performing building that would be the forefront of energy efficiency and green design. This coincides with our overall team goals to create a sustainable structure that will stand the test of time, a quality design that meets the functions of the occupants, a cohesive design that integrates the different engineering disciplines while also complementing the pre-existing architecture of Texas Tech, and an innovative design utilizing new engineering techniques.
Shown here are the guiding codes and standards that were used during the design of this facility. And now we'll move into the structural discussion. We'll first review our gravity design, followed by our lateral design, foundations, special considerations in terms of the project challenges, and conclude with our cost considerations and a summary of the design.
The upper roof gravity system consists of trusses spanning east and west, bearing on girders over the bleachers and hangar door, and bearing on columns everywhere else. Steel joists span between the trusses with metal deck above. The arched roof trusses span 200 feet from outside wall to center dividing wall and were designed using ram elements. The design of a curved top chord and slope bottom chord allowed for a 10-foot truss depth at each end with a 15-foot depth at the center of the truss where the maximum moment occurs. The top and bottom chords are wide flange members and the vertical and diagonals are HSS tubes. The steel joists selected are 18 K6 open web steel joists, and they span 30 feet between each truss. The deck we selected is 1.5D 16 gauge Wellcraft steel deck. The thicker gauge was needed for diaphragm strength and impact resistance. The largest girder is located over the hangar door in the center wall. There are 12 trusses framing in from the football and track roof that frame into this girder, which spans 150 feet. 9 different girder geometries were analyzed to determine the most efficient design. The final design selected was one of the lightest iterations and also provided for the most practical truss connections. Deflection was a major consideration for this girder so as not to interfere with the hangar door below. Using a 40-foot deep girder, deflection was limited to 3/4 of an inch. The track bleachers are located directly below another truss-bearing location, so another 150-foot long girder was needed to transfer these roof loads across that opening to columns on either side. The depth of this girder was kept as shallow as possible in order to provide an unobstructed view for spectators in the bleachers. The end wall on the north side of the track has a girder that spans 174 feet over the main entrance to the facility. This girder is much smaller than the others, as it only has to support roof loads over half of one bay.
In addition to the upper roof, the Performance Center also includes various low roof elements around its perimeter, the most notable of which is located on the north and west facades of the building. To minimize overall member weight while still maintaining adequate capacity, a combination steel joist and deck system was used for this roofing area. To further maximize member efficiency while minimizing the overall number of cross sections used on the project, this low roof area was subdivided into 3 separate sections. The first section is located over the weight room. The second section extends over the main entrance to the facility, and the third section is located over the fixed track bleachers. In wanting to maintain an open floor plan in the weight room, that first section there, the structural team utilized long span LH series Volcraft joists for a controlling span of 56 feet. Typical of all of the subsections, the open web steel joists will frame into wide flange members, and these members will in turn connect to the gravity columns of the system. Where possible, we designed these gravity columns to be HSS just to limit any possible interference with the proposed architecture. The overall result of this system provides the university with a secure, resilient structure while still allowing for reduced cost and construction times.
In designing the lateral system, we studied both moment and brace frames. From this study, we determined that brace frames would be best in this situation due to the high wind loads, and being that brace frames are typically controlled by strength rather than serviceability. Shown here then are the east, west, and north-south systems in our facility. In this, we had to consider obstacles in placing the brace frames, we had to consider obstacles such as the arcaded windows along the low roof and the glass walls and garages on the east wall. Additionally, we considered trying to spread the brace frames evenly throughout the structure to minimize torsion about the center of rigidity of the structure.
With the ETFE over the track and the nearly 200 skylights over the football field, much of the roof diaphragm was removed. To transfer lateral forces from high wind speeds from a EF3 tornado, additional framing was required around these openings. A horizontal truss composed of wide flange beams and HSS braces was placed around the ETFE, the perimeter of the ETFE opening. On the football side, HSS tubes were used around to frame in the skylights to transfer forces around these openings. Integrating the ETFE and the skylights into the roof diaphragm design was challenging. However, it allowed us to achieve a high performance design and gain LEED and WELL credits through additional daylighting.
Shown here are the wind design parameters for the facility. Being that the owner required the facility to be an EF3 resistant structure, we chose to design the lateral system to the 167 miles per hour instead of ASC 7's basic wind speed of 120 miles per hour. In addition to that, we have a safe room that is designed to 250 miles per hour and will be discussed later by John. Shown here then is a typical brace frame. We use W shapes for the beams and columns and HSSs for the braces. Additionally, shown here is a table of drift limitations for the different roof heights throughout the facility. And as you can see from that table, our limitations were not exceeded, thus resulting in an adequate brace lateral system in terms of serviceability.
The facility is supported by 84 drill belt shafts, which are connected by a series of 48-inch deep grade beams. As well, over the building footprint is a 6-inch slab on grade, except for at the football field, which is compacted fill. This was thanks to coordination with mechanical and their ability to design radiant flooring within the compacted fill. There are 4 drill belt shaft designs, the smallest being the first design. This is typical of our north and south facade, as these are seeing lower gravity and uplift loads. The second design is typical of our east and west facades, as these are seeing the higher loads from our trusses spanning from the east and west, as well as the interior columns. At the girder over the bleacher and the entrance to the track is the third design to support both of those girders. The largest design, the fourth, is at the hangar door with the largest girder spanning over that, as well as this foundation is pounded 10 feet deeper due to high uplift seam. Each of these designs are utilizing 1% gross area of the shaft for steel reinforcement. Here are the 3 grade beam designs. The typical is the first design being 30 inches in width, which is most of the facility. With the second design at the safe room, this was widened to ensure that the safe room wall as well as the facility wall could adequately sit on the beam. The third design was needed at the brace frames to manage the large shears seen in these locations, and is 48 inches. The slab on grade was made possible due to 10 feet of engineered fill over the entire building footprint, and is utilizing number 4s at 12 inches on center each way.
The FEMA-rated safe room is located beneath the bleachers along the west wall of the track. In order to fit a safe room large enough to accommodate the number of people present on non-event days, the finished floor elevation was dug down 2 feet below the track finished floor. The overall dimensions of the safe room are 106 feet by 21 feet 4 inches. There is a generator room in the northwest corner, and their safe room has doors and ramps on the north and south ends. The design wind speed for the safe room is 250 miles per hour as specified in FEMA P361, with a required minimum roof live load of 100 pounds per square foot. The actual roof design was based on a conservative calculation of the weight of the superstructure that could potentially fall on the safe room. The safe room walls are 12-inch CMU fully grouted with number 5 bars at 8 inches on center. The roof consists of 12-inch hollow core with a 4-inch concrete topping, and the hollow core spans the shorter dimension varying along the long east and west walls.
As discussed by Dana and John, the entire facade of this structure has been designed to resist the wind forces seen by an EF3 tornado. The table shown here is from ICC 500, and it actually outlines missile impact testing, which is basically you take a 2x4 and you shoot it out of an air cannon at 84 and 56 miles an hour, depending on if we're testing vertical or horizontal surfaces. So for the main exterior perimeter, up to a height of 21 foot 4 inches, brick veneer wall on steel studs was used. And from testing done at Texas Tech itself, this sort of structure can resist wind speeds or missile impact speeds up to 120 miles an hour. So that far exceeds what we need. Above that 21 foot 4 inches, there is a plaster stucco over standard construction grade plywood. From investigation of this, a typical wall frame wasn't able to resist those wind speeds that we needed. So in addition, another sheet of that 3/4 inch plywood, as well as 16 gauge, flat steel will be included in these areas. Through investigation and discussion with Thornton Tomasetti, who happens to be one of the leading ETFE engineering firms in the country, especially for sports facilities. It has been shown that that membrane will exceed any sort of impact debris seen by an EF3 tornado or hurricane.
The structural estimate then came into a total of $20.8 million. This includes all of our add alternates that we are considering as our project challenges. If we take out the add alternates from this, we could reduce our budget by approximately $3.4 million. The add alternates structurally include our EF3 wind speeds, designing the extra steel required to resist those speeds, as well as including a safe room under the bleachers. And with the ETFE, we had to include the additional diaphragm to transfer our loads rather than being able to depend on the deck to do so. So the additional steel required for that, as well as the additional framing around the skylighting. So in summary, our proposed structural design meets the project challenges set out by our client, as well as our team goals that oriented with those project challenges. These goals then are the sustainability, quality, cohesiveness, and innovation.
And now we'll move on to the mechanical portion of the design. First, we'll discuss the primary and secondary systems, followed by advanced engineering solutions, high performance design, resiliency and security measures, followed by a summary. Texas Tech Sports Performance Center utilizes its own dedicated primary system located underneath the football field and track and field area. This adds to the resiliency of our facility. This geothermal well field consists of 320 wells, roughly 400 feet deep. A GLD analysis did take place to make sure there was proper sizing of the well field, as well as to accommodate ground rise temperature over a 20-year span. Coordination with structural took place to ensure that the well fields did not interfere with their drill belt shafts. As you can see, we were able to locate our well fields in a way that did not interfere and will help move along the construction process that will be touched on later.
The geothermal well field supplies heat rejection and heat regeneration to our bank of multi-stacks heat recovery chillers. This modular chiller system can be quickly installed, and it also can be used as staged compressors to allow for high efficiency at part load conditions. The hot and chilled water loops utilize modified single loop systems. The chilled water loop shown here shows that chilled water is first delivered to the AHU units and then to the chilled beam and radiant floor zones. This allows us to move to use a lower head loss on the secondary circulation pumps, and also reduces installation time since the single loop pipe sizing is the same size throughout the building. At the chilled beam zones, we utilize TACO's low flow mixing blocks. These use zone level pumps to regulate the temperatures in the chilled beam zones, allowing us to maintain our desired temperature. At the radiant flooring systems, we use injection pumps to inject hot and cold or chilled water from the desired loop into the radiant system loops, and the radiant system circulation pumps then keeps that temperature at the desired, at our set point. And the single loop system also, because it uses zone level circulation pumps, it reduces the balancing time required once the system has been finished. The building is served by 4 air handling units that serve conditioned air to the spaces. AHU-1 serves the chilled beam areas on the north side and northwest corner of the building. This unit supplies dry dehumidified air to these spaces to account for the latent and ventilation loads. AHU-2 is a dedicated dehumidification unit that serves just the hydrotherapy pool. These 2 units are located on the low roof section on the north side of the building, but are concealed from view of pedestrians by the sloped roof. AHUs 3 and 4 serve the football field and track and field respectively. They are housed in the AHU units at the south side of the building. These 2 units and AHU-1 utilize a second desiccant wheel in addition to the primary energy recovery wheel. This second desiccant wheel wraps around the cooling coil to provide increased dehumidification and reduces the reheat energy requirements. AHUs 3 and 4 are also paired with radiant floor systems to provide for the remaining sensible heating and cooling loads of the fields.
And now to talk a bit more about our secondary systems and why we chose them. The chilled beams located in the north and northwest rooms were chosen over a traditional VAV system because they are able to reduce the amount of ductwork necessary, reduce overall fan power, as well as increase the thermal comfort in the space. Utilizing the TACO mixing boxes, we're also able to reduce our piping that a normal chilled beam system would utilize. The chilled beams will be paired with dew point sensors located in the zones they serve. The radiant flooring is in the track and field and practice field area. This hydronic system is known for its increased thermal capacity, making it very efficient. It also increases the indoor air quality in the space since you don't have large CFMs moving allergens and pollutants in the air. Due to there not being a concrete slab in the practice field area, a different construction process had to be thought of. So Mechanical utilized a system similar to what is shown, utilizing the radiant flooring within a sand bed underneath the turf. As you can see below, the systems allowed us to have savings in ductwork, fan power, space cooling energy, and fan energy. There is an increase in our overall pump energy due to this hydronic system, but allows us to save mechanical energy overall. Displacement ventilation will be paired with the radiant flooring in the track and field and practice field location. This accounts for the latent load. By utilizing displacement ventilation, we're allowed to decrease our outdoor air requirement by 17%. However, we are supplying 10% more than what is necessary to increase occupancy comfort in the space. This will be paired with demand control ventilation, utilizing CO2 sensors in the space.
By being able to move the west wall, by extending the west wall, we were able to move the domestic water and fire suppression entries from the east side of the building to the west side. The main mechanical room is located in the southwest corner. This room houses the major hydronic equipment, including the geothermal heat recovery chiller bank, the primary and secondary circulation pumps, and the geothermal well field header. The AHU units are housed on the south side of the building in the two AHU rooms that were expanded to accommodate these large units. These rooms also accommodate the hot and chilled water circulation pumps and the hot and chilled water injection pumps and the radiant flooring circulation pumps. The facility is classified as an A4 assembly light hazard facility. The building was divided into 4 fire suppression zones, shown here on the right. On the left is a detail showing the fire suppression entry into the building. By being able to move the domestic water entry to the west side of the building, we're able to minimize the amount of piping needed to deliver domestic hot and cold water to the plumbing fixtures due to the adjacency to the 2 major consumers, the 2 large restrooms. We're also able to reduce overall water consumption by 44% based on the LEED version 4 calculator. To maintain a high quality of water in the building for our athletes, the water will be run through an activated carbon filtration system that will remove unwanted particulates from the water. The hot water for the building will be heated from a loop from the hydronic hot water supply. This will be done using a hot water tank with an integral double-walled heat exchanger. This double-walled heat exchanger prevents cross-contamination between the domestic hot water and the hydronic hot water systems. And also, for the low roof areas and possibly for the large roof areas, we're looking at using a siphonic drainage system. This system allows us to use smaller pipe sizes for rainwater drainage and also decreases installation time and installation costs. To ensure a high quality of acoustic performance for the space, the systems that we chose were traditionally low noise generating. The chilled beam units and the displacement ventilation diffusers were sized to have NC levels no higher than 25. The main mechanical room and the AHU rooms were also decoupled from the main structure, and the equipment inside use vibration isolating techniques, including equipment pads, spring isolators, and flexible connections. Here are shown some of the design calculations we used. On the right is the ventilation calculation taken from ASHRAE 62.1. As Danielle said, we used displacement ventilation, and so we're able to increase the EZ value to 1.2, which reduced the total amount of outdoor air we had to bring into the facility. On the left, we have some of our radiant floor calculation sizing. By solving for the GPM required to meet the sensible load of the space, we take that GPM divided by the number of loops in the space, and then based on the loop length and the industry standard of a max pressure drop of no more than 10 feet of head in a loop, we're able to size the hex piping in those areas. For both the football field and the track and field, we sized our radiant floor piping at 3/4 inches. As we're designing our systems, we wanted to look for new and innovative technologies that we could utilize to make our systems better. For the hydrotherapy pool, we found Dryden Aqua's green glass activated filter media is 30% more efficient at filtering organics over a traditional sand filter, which leads to many benefits, including reduced chlorine consumption, and also eliminates that chlorine smell that's typical of most pools. On the air side, we utilized Dynamics V8 air cleaner system. This This system uses activated field technology to ionize the media fibers and the particulates in the air to increase filter efficiency over standard filters. Additional benefits are lower static pressure drop over traditional filters and longer filter life, which ends up resulting in fewer maintenance costs for the life of the filters.
For the ETFE system, coordination with the electrical team had to be done to ensure that while there will be a thermal heat gain load in that area, that it doesn't impede in our overall goal of energy savings. We were able to come up with a compromise of a 4-layer ETFE system. This system has 2 inner layers that can open and close based on the time of day. As you can see, we were able to input the solar heat gain coefficient values into our energy model to ensure it didn't impede our savings. The ETFE is inflated by 2 inflation units, each unit containing 2 fans, but only one of which is running at a time. The only reason for these inflation units is to maintain pressure in the cushions, not keep airflow going through it continuously.
Ventilation to the safe room is provided from 2 louvers. One big one on the south end is an intake louver, and an exhaust fan over a second louver towards the north end adjacent to the bathrooms. The generator room is served by 2 louvers, an intake and exhaust louver on the exterior of the building. The exhaust air is ducted from the face of the radiator into an oversized duct to the exhaust louver on the exterior. This duct is oversized to account for the fact that the emergency generator's radiator fan is not going to have a high static pressure value.
We were overall able to achieve a high performance design with our mechanical systems, saving 55% energy from the IECC 2012 baseline. We reduced our CO2 emissions by 90% and bringing our energy usage intensity down to 13. On the right, you can see a breakdown of the proposed mechanical design energy usage versus the IECC 2012 baseline. Some BE items we can propose to the owner to save money would be to minimize the ventilation and code requirement in the track and field and practice field area, as well as switch out the filters in the HUs and hydrotherapy room to code minimum requirements. We did a cost analysis, and in the end, the mechanical budget is $6.9 million with a 16-year payback, making this system both energy efficient as well as economical for our client. To summarize, the mechanical design was able to create a resilient mechanical system that was able to have a payback period of 16 years, a cohesive design that was unobtrusive to the architecture of Texas Tech, and while saving 55% energy from our baseline.
Now we'll dive into the electrical systems. We'll start with our power distribution and our solar energy, move on into our electric lighting and our day lighting. We'll follow that with the special systems, and finally our cost considerations. Here you can see our primary pathways. We draw from the university at our utility entrance. This feeds our 2000 amp main switchboard, which feeds our various panels spaced throughout the big open area to reduce voltage drop, keeping the panels close to the loads that they serve. You can also see our emergency generator and our emergency pathway underneath the bleacher. Our emergency systems are fed from a 400 kilowatt diesel generator and 9 Tesla Powerwall batteries. The batteries are for in case the generator goes out. These batteries in the generator and also our transfer switches are housed in the generator room in our safe room underneath the bleachers. This feeds our emergency system, which feeds the safe room, egress lighting, and fire alarm, our legally required feeding more lighting and our security system, and our optional standby, which feeds our coach's office and our data storage. This is our riser diagram. You can see on the northeast exterior, we have our utility transformer, CT cabinet, and meter. Here we have our generator room. You can see our 400 kilowatt diesel generator, our transfer switches, and the Tesla power walls. Here's our main electrical room with our MSB feeding the various panels. You can also see the re-rev panel, which is connected to the re-rev generators in the weight room, generating electricity from our cardio equipment. Here are various panels throughout the space. On the west exterior, we have a TV panel, which TV trucks can connect into for broadcast events. And finally, we have our PV array on the roof, which connects to our MSB and provides supplemental power to our Powerwall batteries.
The PV array on the east roof consists of over 1,600 modules, generates 695 megawatt hours of energy annually, and reduces CO2 emissions by 538 tons. Cardio equipment within the weight room have been supplied with a re-rev generator. The re-rev generators act as a secondary power source to the weight room. The re-rev generators also come with a heads-up display that show the athletes how much power they're creating during their workout. The facility backup generator is located within the FEMA safe room and is isolated there. It provides up to 7 days of backup power to the facility. The Tesla Powerwalls batteries are also located within the FEMA safe room and supply 2 days of power to that area. On the west wall of the safe room are receptacles where individuals can charge their devices. And also a distributed antenna system allows individuals within this small area to stay connected with the outdoors.
Athletic success comes through persistence and determination. Our lighting design sought to engage the athlete, drawing them into the space and to sustain them on their journey to greater glory. In the exterior, the bell tower is dramatically lit with wall-grazing LEDs, creating a landmark within the campus fabric. And red floodlighting in Fieldhouse area creates a red ambiance for the red Texas Tech colors. Moving closer to the entrance, in-grade LED grazers illuminate the arcade, and the main entrance is framed with LED strip lights. Moving inside into the main corridor, lines of lights in the pattern to the melody of the Matador song, a Texas Tech fight song, guide the athlete and cheer them on into the weight room at the end of the corridor. These lines of light are actually LED strips inside of built-in coves. And we used in-grade lighting again to echo the exterior. And at the end of the corridor, the frame is illuminated with an acrylic LED strip assembly. Moving into the weight room, you'll find a high performance and exciting in a uniquely Texas Tech Red Raider environment. And moving through the space, you'll notice the re-rev generating bicycles are actually illuminating the logo, creating an interactive and an exciting environment for these student athletes. In the track and field area, we provided diffuse illuminance for practice days, sufficient for the athletes. And then during event days, LED sports lighters illuminate the track and field, meeting the guidelines for NCAA and ESPN standards. As you can see in this illuminance map, the uniformity has met our guidelines and also exceeds 100-foot candles. As well, in the football field, we've exceeded at least 50-foot candles, which is the NCAA recommendation. We wanted to provide controls that were flexible and easy to use for the coaching staff. In this case, this control can actually adjust the color temperature, simulating different times of day if so desired. Our control schematic allows the user the flexibility required for each space's unique requirements without being too complicated. Also, life safety was very important, so in these egress paths throughout, we provided lighting and emergency lighting to help the occupants escape if so needed. As you can see in this illuminance map, we've met the illuminance and uniformity requirements for the track and field area. And also in the football field, we've met those guidelines.
The ETFE over the west roof allows diffuse sunlight to enter on top of the track and field area. This greatly reduces the amount of electrical light needed during occupied times, and the energy savings is 241 megawatt hours annually. Similarly, diffuse skylights over the football field allow light to enter in, reducing the amount of energy by 107 megawatt hours annually. On the east facade, we've placed frosted glass to allow the athletes to practice in privacy and to eliminate glare in the mornings when the sun is rising. On the west facade, where the offices are located, we've installed electrochromic glass to ensure that glare is minimized in the evenings when the sun is setting.
There's a server in the video control room for the FitGuard Impact detection devices, which are integral to the mouthpieces that the football players are already wearing. These sensors will light up if an impact greater than the safe threshold is sensed. The data collected by all of these mouthpieces is stored on the server in that control room and can be accessed by mobile devices. In addition to the usual security implementations of card readers and keypads and security cameras, extra measures were also taken, such as glass break sensors and panic buttons, to aid in achieving the security and resiliency project challenge. You can see the layout of the fire alarm system here, and the fire alarm control panel is placed in the main electrical room towards the north central part of the facility, with the fire alarm remote annunciator placed by the south entrance of the football field, since that is where the fire department access is located. Here you can see the layout of the data system. The university is its own ISP with a redundant loop going throughout campus, and the building taps that loop at the ISP entrance indicated here. And you can also see the layout of the wireless access points, which were placed with a 75-foot coverage radius. Here you can see the layout of the AV devices. In the football field, the speakers were placed on the wall as opposed to on the ceiling to avoid footballs going through the air, and also have been protected with wire guards to minimize damage. And the conference room and the coach's office have been provided with video conferencing capabilities. A video display board and a scoreboard are located in the south end of the track and field area to keep event attenders up to speed on event days. Hardwired junction boxes have been placed all around the track and field area for TV broadcast cameras to plug into to ensure adequate coverage of all events. These hardwired boxes then connect back to a patch panel towards the northwest portion of the building, which then connects to the existing to remain TV broadcast junction box on the northwest exterior of the facility. Here you see a section of the enclosure for the TV broadcast equipment on the northwest exterior, showing the transformer, the panel, and the 4 Goldwing disconnect equipment pieces. A distributed antenna system was also provided in the facility, with one of the DAS systems covering the entire building and a second dedicated system for only the safe room. And the antennas were placed with a 150-foot coverage radius. Here you can see a lightning risk assessment, and given the parameters of the building, a lightning protection system is required. VE options available to the owner include only providing a distributed antenna system in the safe room. The contractor can also implement modular wiring strategies, and aluminum conductors can also be used instead of copper conductors with ampacities of greater than 100 amps. The electrical cost considerations come out to $4.7 million, and that includes the materials and labor for power, lighting, and special systems, as well as contractor miscellaneous costs such as job site trailers, permits, tools, and overhead and profit. In summary, through the implementation of ETFE, the skylights, the PV panels, the generator, and the Tesla power walls, the electrical design team has met the project challenges.
Now we'll move into the integration portion of our presentation. We'll first go over our integration items, and then we'll touch on our project challenges of resiliency and security, a high-performance design, and an accelerated schedule. We'll conclude this with our value engineering options and a total summary of our design. The architectural changes provided previously allowed us to make integration alterations as a team. All the architectural changes that we did end up implementing within the facility were confirmed through coordination with each discipline to ensure that these architectural changes would not hinder the architecture, the site, or any discipline in a negative way. With that, we were able to extend the west wall out 5 feet, allowing both the safe room and the generator to be located underneath the bleachers. With the additional space on the southern wall, we were able to include additional mechanical space, as well as increase the AHU rooms for those units. Lastly, you can see the cutouts here of the ETFE overlaying the roof, as well as the skylights over the football field.
The layout of the roof was coordinated between all disciplines to ensure success. A 10-foot perimeter around the edge of the roof was kept clear of all equipment to avoid needing a guardrail which could disturb the architectural design. PV panels were placed only on the east side of the roof because that is the higher side and therefore would not be shaded anywhere near as much. In between the PV panel walkways, the skylights were placed and were rated with the capacity to be walked on by maintenance personnel, And those skylights were placed in between the trusses and the joists to ensure that the daylight entering the football field was unobstructed.
In designing the ETFE roof, we worked through multiple iterations as a team to determine which would benefit each discipline the most. It was determined first that if we wanted to include ETFE, the structural team would have to accommodate with the diaphragm. So the structural considerations were considered a minimal impact in determining which would be the best. So the first iteration shown here covered the entire roof over the track. While this did significantly increase the daylighting, thus reducing electrical lighting, it significantly increased our mechanical load, making it not an optimal choice, which led to our second iteration. We included strips of ETFE across the track roof. While this did decrease the thermal load enough while still increasing the daylighting to make it adequate for our energy savings, it was deemed not feasible due to needing separate inflation units for each strip. Which brings us to our last iteration of a 36,000 foot square membrane hovering directly over the track. This iteration allowed us to optimize daylighting, reducing our electric lighting by 86% on non-event days. Additionally, was a compromise, but we were able to implement this to better our system as well as gain lead and well credits. And lastly, this only affected our budget by $2.75 million, but we're including that in our add alternates as this accommodated the project challenge was set by the client.
Our goal was to create a high-performance design. So to do so, we used LEED version 4 as well as WELL building standard to measure our high performance. As seen in the boxes below, with each box roughly counting for 2 points, we were able to obtain 62 LEED credits with another 24 additional points that are based on owner implementation and motivation post-construction. For WELL credits, we were able to achieve 65 of those, again, assuming some owner implementation, with an additional 26 possible that the owner can implement at a time of their choosing. This helps us achieve LEED Gold accreditation as well as WELL Gold accreditation with the ability to achieve LEED Platinum and WELL Platinum. To focus more on WELL building design, we wanted to really focus on the health and wellness of our occupants. The addition of the ETFE roof helps us win innovation points within WELL standard because it allows the occupants to be connected to the outside environment through the system. The ETFE also utilizes 100% recyclable material. For the hydrotherapy room, utilizing that water filtration system helps reduce the trichloramines within the pool area as well as the chlorine smell, not only improving the water quality in the space, but also the air quality that the occupants would be breathing.
An energy display monitor is placed by the fueling station, which gives a visual indicator of the amount of energy produced by the PV panels, as well as the amount of energy saved by the ETFE, the skylights, and the geothermal well fields. To aid in meeting the well features for lighting, luminaires were specified with a CRI of at least 80 and a color temperature of 4000 K to help in achieving the melanopic equivalent LUX feature.
And lastly, the dynamic V8 filters located in the AHU coils helps increase the indoor air quality within the environment, having better air for our occupants to breathe and really paying close attention to our athletes in the space. Overall, our building has numerous reductions. We were able to save 86% in electric lighting load due to the combination of the ETFE and skylights. We were able to reduce our energy savings by 25% due to the solar energy the photovoltaic arrays help create. We reduced our overall CO2 emissions by 90% and our energy savings by 80%, saving roughly 7.7 million kBTU annually. For an accelerated schedule to keep in mind, we decided to go with a design-build approach. This approach brings the engineers and contractors on earlier in the phase to get rid of that time where you'd normally be bidding out a project. Each discipline also implemented several time-saving measures within their designs.
To aid in the accelerated schedule, the structural team utilized a typical truss design over both the track and football field. This allowed for a total of 4 different member sizes for every single truss within the facility, allowing for a repetitive construction process throughout the construction of the facility. Additionally, we worked to release packages early throughout the design stages and procure our steel materials early on.
To minimize lead times, luminaires were specified from as few manufacturers as possible. As a result, the high output lights needed for the track and field area and the football field were specified from spec grade, and the lighting for the rest of the areas were specified from Cooper lighting.
For mechanical systems, we chose non-mats for our radiant flooring installation, which will increase the overall installation time of providing this type of system. Also, we coordinated our geothermal well field design with structural. So the drill belt shafts as well as the geothermal well fields could technically be drilled out during the same time. Some value engineering items we can provide to our owner would be to focus on owner-controlled well optimizations. This would put it on the owner to implement these whenever they so desire after construction, leaving it out of our budget. Another option would be to combine mechanical and electrical construction processes, such as trenching out for conduits as well as mechanical piping at the same time. The third option would be to reduce our photovoltaic array by 50%. This still allows us to achieve a very high-performing building, but will reduce the overall cost of that system. In the end, our cost for all 3 engineering systems comes out to $35 million, and that's including the add alternates that meet the project challenges. If we take that away, our estimate for this project is $28.1 million. To sum up our design, FLUX Engineers was able to create a sustainable and long-lasting design that has a FEMA-rated safe room and a dedicated primary system located underground. We were able to create a quality design for $35 million that meets the client's challenges. We were able to blend our interdisciplinary designs to create a cohesive design for this facility that already blends well with Texas Tech's freestanding architecture. And lastly, we were able to create an innovative building that had 80% energy savings from the ICC 2012 baseline and achieved LEED Gold and WELL Gold certifications. With that, we thank you and we'll open it up for questions.
As we did previously, I'd like to open the floor to our remote evaluators and mentors to get their questions asked first.
Okay, I'll go ahead. If you could go to what slide? The one where you have the generator, please. I think
That's the safe room slide.
Yeah.
Yeah. This one.
Is this the correct one?
Correct. Is that in an enclosure as you have shown, or is it? Are you specifying it with the enclosure? Is that correct? As opposed to just the genset?
Yeah.
Okay.
Yes, correct.
Is there a particular reason?
To aid in keeping the exhaust away from the occupants in the safe room.
Okay, and then is there? So I assume did mechanical design exhaust outside of that to the exterior?
Yep.
Okay.
Yep.
Just double checking. And then how many gallons fuel are you storing?
The size of that tank, we don't have a final estimate on that size, but it will be adequate to account for the 7 days of usage that's required by the project.
Just to let you know, there might be a limit on how much you can store inside a building at the tank. I don't know if that, I'm not exactly familiar with all of it, but I know on the project I am working on that we had that issue, so you should look into that.
Correct. The location of the tank is actually going to be on the exterior. It's going to be underground.
All right, no worries then. I had a question for Nick on the bicycles powering up that logo. What happens?
Yes.
What happens if nobody is bicycling?
So actually, there's more of a static or like ambient sort of mode that it goes into when no one is using it. But when somebody is activating and using it, the brightness will increase dramatically and add for more of an exciting environment. But if, like, say, somebody or a visitor or a fan is walking by the space outside and looking in, it's still going to glow and create sort of an inviting experience for them as they observe it.
Perfect. All right. I was just curious. And then for in the space for your daylighting calcs, did you account for the skylights providing some shade on the skylights? Sorry, I said skylights. PV onto the skylights, shading the skylights.
No, because those were specified to be mounted flush with each other, and so they will not shade the skylights.
Just in your image, it's different, so that's why I was curious.
Okay.
Thanks.
Yep. Thank you.
All right, I have a question for the mechanical team.
Yeah.
And it's again on that slide with the generator, the one Jeff had you pull up first. Could you guys tell me what the heat load was from the electrical team's equipment in that room? I saw you had the battery packs on the wall, and then I guess that generator is in a separate room, but could you guys tell me that?
Correct. So for the actual safe room, they're providing ventilation through separate louvers. And then in the generator room, we focused on, is that a dog? We focused on the exhaust and intake specified for these generators in that area.
I might have missed it. How are you guys dealing with the heat from the battery packs? Because it looks like those are directly in the that safe room.
So the battery packs are in the safe room, that's correct, not in the generator room. And those are actually specified to be not giving off heat in those kind. So that will not be an issue with that specific model.
The Tesla Powerwall 2 also has an integrated water cooling system within it, which greatly reduces the amount of heat.
Okay. And where's that heat dissipated to?
That's something we'll have to.
It's cooled internally. So, I mean, it's not really emitting large amounts of heat at all.
Okay, and maybe I'm understanding it wrong, but I think that heat would have to be transferred somewhere. I just would check into that. But.
We'll look into it. Thanks, Mike.
Can I add something there? If they are water cooled, you guys on the mechanical team will need to provide some sort of connection for that.
Okay. Yep.
Other questions?
I've got a question. Could we turn to the egress path image with the lighting?
Life safety path?
Yeah, life safety path, excuse me. So it looks like your broadcast truck, when it's on site, if it's shown where it was, maybe blocking one of those, the northwest egress path door, just north of the stands, where you've got it shown on, if you go to that broadcast booth or the broadcast truck slide.
So the rectangle in this slide is not exactly to scale. It'll actually be a little further to the left as we're looking at it here. There's a pretty wide sidewalk between the edge of the building and the parking lot where that truck will be parked. So occupants, if they have to leave on that egress path, will have ample room to make it out onto that sidewalk and to evacuate safely.
Okay, yeah, just might want to make that a little clearer on your diagram, and also be considering where they're going to have all of their cable communication and power cables, if that's going to cause a potential tripping hazard.
Yeah, that's a very good point about the diagram. For the cables, they're actually going to be connecting from the truck up to the northwest to that exterior junction box, which is then connected into the facility through underground lines. So on the path of egress, thankfully that will not be a tripping hazard with the current layout.
Okay. And then on the design build approach that you mentioned, you just briefly talked about, you'd have time saved on construction, but you don't go into what the estimated time saved was, nor did you talk about what packages you would consider releasing early to help with the time savings. Just think that perhaps adding that detail would help in that presentation.
We can definitely look into the packages provided. As for a specific amount of time saved, we'll probably have to discuss more with a contractor since it's kind of outside of our knowledge, but we will definitely try and get a number.
I understand you don't have CM on your team, but it could be strengthened. That's all.
Thank you.
Thank you.
While on this slide, I have a question about that lighting part of it. How does that specifically speed up construction by limiting the number? It would be each of these has to have a quick ship option if you did that. And then how do you balance that with getting an appropriate bid? Because if you sole spec something, that price will probably increase.
So the intent with this one was to minimize the points of distribution, and therefore if they're all coming from the same manufacturer, the intent was to be coming from the same distributor. And Cooper Lighting is a wide enough brand, we figured there'd be no issue down there around the area of the project. And also even within Cooper, it was considered as far as the cost of the individual brands under that Cooper brand. So like the more expensive lines such as Shaper and that kind of line were not implemented, whereas an emphasis on the more cost-effective lines were implemented. As far as the fairness in bidding, that's a very fair point, and that'd be something we would just need to address with the contractor at that point.
Yeah, I mean, you could do an alternate manufacturer or something like that, but I would just mention that kind of aspect.
Okay, thank you.
To kind of piggyback on that comment, I think something to look at instead of, speccing from a specific manufacturer rep is looking at your different types of fixtures. Are there any ones with an exceptional lead time on them that you need to identify? And that would be something to communicate to the contractor that's like a priority submittal that you need to get sent through so they could release that.
Okay, thank you.
Other remote questions?
You have several truss.
Sorry, what was that?
Can you repeat the question, please?
My question involves the structural system. You have several long-span truss systems, like the one that's illustrated in the present slide. Under wind load and dead load load conditions, is the net load upward?
No, it's not. With the weight of the roof and the structure, it was the net load with the load cases was not upward.
There's some stop time.
Questions, local questions?
In your summary, you had identified 7.7 thousand BTUs saved annually from your implementation. 7.7 million? Okay.
10%.
I was just curious if you had applied what a dollar figure would be to that to see if we integrated all of these items, what their payback would be with these cost savings.
Correct. For mechanically, I know in a 50-year time span, the client would save 1.6 million overall. We didn't do it for the overall cost, but I think for the, at least for the energy saving portion, it would be easy to come up with a number for that. Yeah, thank you. No, yeah.
Okay, I've got a couple questions for you guys. Your big girder over the inner door, why did you limit the deflection to 3/4 inch for 150 foot speed?
With the hangar door below, we didn't want the girder to deflect too much to pinch those doors in any way. So from the top of the roof to the bottom of the girder is 40 feet, and then there's 10 feet below that to the top of the doors, which would just be infilled with framing and bracing for whatever bracing is required for that door. So we just wanted to limit the amount that it could potentially deflect so it wouldn't interfere with that door.
Okay, I was more or less testing you there to see if you considered the deflection of that on the door. Also, for your storm shelter, a couple of questions in there. We've got a 12-inch block with number 5 and 8.
Yep.
With 12-inch CMU, you can utilize bars on each face.
Okay.
Would you end up not, I don't know, with the FEMA wall requirements that you guys have for impact testing, you may need bars at 8 inches on center regardless, but it at least could be a design consideration that you could do number 4s to, number 4 on the outside face and inside face at 8 inches on center, rather than doing number 5 center.
Okay.
It just gives you a bigger lead for the washer.
Yeah.
Really.
I think that's.
And then for your louvers, kind of a question between mechanical and structural. We've run into a problem on a couple of storm shelters that we've done, where A, you need to make sure that the louvers are rated for being a storm shelter.
Correct.
And B, you need to distinguish who's responsible for the physical attachment between the louver and your jams or headers or sills. There's quite a bit of controversy. Mechanical doesn't want to do it because it's a structural connection, but structural doesn't have anything to do with the louver. So just be mindful that you'll have to have that discussion. Yeah.
We'll definitely look into that going into CD.
Thank you.
I had a couple.
Question on the structure. Question again?
Sure, go ahead.
Okay, on the structural system, did you compute your loads by hand, or did you have them automated?
The calculation of the loads. Individually, we did calculate like our respective dead and live loads, as well as we determined the load combinations that we'd be using. And then while using different applications such as RAM elements to help with the design of different elements, you can implement your own individual loads and the load cases that you're using to design whatever element you're designing.
And approximately what was your roof dead load per square foot on your main areas?
Including the weight of the truss or excluding the weight of the trusses?
It was, yeah, 25, not including the weight of the structure. 25 pounds per square foot.
Just for the roof?
Yep.
Thank you.
I had a couple structural questions too. On the trusses, it looked like you had a lot of wide flange sections for the cords and then tubes for the weld members. Have you guys started looking at connections at all on those? And I guess where I'm going with it is as far as your construction speed and cost too. Bolting of that kind of stuff is usually significantly faster and you got a lot of it. So have you looked at that at all yet?
We have not started that yet. So you'd recommend bolting?
As much as possible. Yeah, it might be something you could take advantage of. If it works out, you could take advantage of in your construction schedule too. Contractor might be able to give you a good guidance on how much that really saves them, especially if those long span trusses might have to ship in several pieces and then weld up in the field. That would be pretty time consuming and you gotta have a crane hold it and all that. And the second one was on your foundations, the drilled shafts. I was just curious what the capacity was based on, I guess, because I was just running some quick numbers and it seemed like the bearing pressure was really high.
Yeah, so the bearing is probably higher than if you're just doing your area over the allowable bearing. But I included the friction on the shaft itself, and so that got me the higher number.
I have a question from kind of the constructability point of things. ETFE, is anyone within that area as far as contract? I mean, is there any other building in that area that has ETFE so there would be experienced contractors in installing that? With the new technology, I'd be afraid that you may have some road bumps to get over.
We have not looked at where manufacturers would be located. I don't believe it's been used previously in Texas Tech's campus, but that's definitely something we can look into and get an answer back.
Well, along with that too, like even if, I mean, I'm a novice when it comes to the Dallas Cowboys, but even if they like use ETFE in their stadium or any stadium in Texas period, it'd be a lot easier to get a contractor, you know, from Texas to take someone's down and go to Lubbock versus having to get somebody from New York. If you're going to want to specialize, or you're going to have a lot of learning curves to deal with.
I can definitely look into if any sports complexes in Texas utilize it.
Yeah.
I have a general question about the electrical generator again. I wouldn't say that the generator enclosure is necessarily a common element that you would see within a building. It's really intended to be standalone outside of a unit so that natural air kind of flows through it. If that is an approach that you want to take and have that enclosure within the building, you still need not just the exhaust, but you need intake air and you need the radiator, you know, louvers appropriately sized. But then also I was kind of looking at clearances. You still need clearances around all sides of your unit. They have access panels and all of that. So typically 3 feet around the generators. So it's a little coordination there. You might be able to save some money and just take your enclosure out and just have it an open generator with the muffler indoors. You can still get, I mean, that's more common for a building like this.
The reason it's located is due to FEMA requirements that the generator needs to be in as secured of an area as the safe room in case of the natural disaster, which is why we went with the enclosed area adjacent.
Are you referring to?
An enclosed area is fine, but you kind of get the enclosure within the enclosure. You know?
Is that what you're
Yeah, the house itself is not really necessary.
Makes sense. Thank you.
I want to piggyback on that. I feel like maybe revisit the whole generator mechanically because there are some elements that are missing there. I don't know how far you guys are required to take it, but you'll have a day tank, a fill station, and kind of considering like when a truck drives up and fuels your underground tank, just develop that a little bit more.
Okay. Thank you.
Thank you.
To go on that a little further, did I miss maybe that's the plan how you get in and out of there?
There's a double door on the north side of that room,
Yeah.
and that opens up into the space in the track and field area.
So what if you have to replace that?
Just one suggestion would be, because I think you do mechanically show louvers, like an intake and exhaust louver for that generator room.
Yeah.
Something to address the replacement would be sizing the louver large enough that you could take it off and replace the unit through that louver, opening it, you know, take the louver off, put it in through the hole, and then reinstall the louver.
Yeah.
Looking at this slide, well, you mentioned that this safe room is below grade, but this image doesn't show any stairs or ramps. Is that located outside of the safe room, or how do you get in?
So the ramps are by both of the doors. They're just not shown on this image. But each of those doors you walk through it and there's a ramp sloping down to the safe room floor.
So that'd be a 24-foot ramp, or how?
No, it's 2 feet. It only goes 2 feet below.
But the length
Long.
to meet ADA would be.
Yeah.
Okay.
Okay,
One
more
question. Where are your inverters for the PV system located?
Those are on the low roof. Do we have an overall view of the plan?
No.
Probably just go to one of the special system slides, I think, and show it. There's a low roof portion towards the north of the facility, the same place where mechanical had one of their units as well, where it's kind of in between the roof and ground level, where it can be placed and accessed by maintenance personnel, but not visible by passersby.
And that allows it to be very close to our main electrical room, which is what it feeds.
Are you saying there's only one?
No, there's
The way you're
multiple.
speaking, you're saying there's only.
There's multiple inverters. They're just placed on the lower roof system there. Yeah.
Are those string inverters?
I'm not sure what that term means, to be honest with you.
Look up single inverters, micro inverters, and string inverters.
Okay, will do.
Okay, thank you.
Thank you.